talk a bit about invertible matrices, and actually it's the same thing if we have a square matrix. It's invertible if and only if there's many conditions. One of those conditions is that rows or columns are all linearly independent from each other, and in both cases they're linearly independent from each other. And there's more ways to check it, but let's have a concrete example, because how we can actually find out the spanning set of vectors, of column vectors that span the whole column space, which is the span of all the columns of a matrix, is by the technique of being able to identify the position of so-called basis vectors. So let's say let's take some simple example. Let's say 1, 2, 3, 3, 2, 1, 5, 8, 9. So if we take this, for example, and we take it over the field, or actually for us to have it even easier, let's do it smaller here. So let's do, for example, 2, 1, 1, or 3, 2, 2, or something like that. And let's say over z sub 5, z 5, which z5, it means integers below 5. That means when we do any arithmetics, we would take the remainder after division by 5 instead of just adding the numbers or dividing. That means, for example, 3 plus 2 would be 0 under these conditions. 3 plus 3 is 6, but we have to divide it by 5 and only write the remainder, so that's 1. That's the idea for Z5. I would definitely recommend focusing on Z5 itself as the arithmetics of that, but we do it to ease up the numbers. And I mean, this is a good example, so we generalize it. This is a field as well. As long as you have prime here, this is a field. It fulfills the requirements. So our goal here is to see, are the columns linearly independent or not? We have 3 columns, this one, this one, this one. And the way we can tell it, we can do row reduction. So we can do row reduction, and let's do that. So I would subtract, for example, twice the first column from the second. I want to see if we have a pivot column in each of these, a pivot in each of these columns. Then it is called a so-called pivot column, which means basis column. And a basis column is the location, even after row reduction, of the columns we can take that will on their own span the whole column space that all the 3 columns span. That means if we take our linear combinations of these 3 columns of the original matrix, if all of them are pivot columns, we need all 3 of them to span the column space of this matrix, which is the span of their columns. Also, it's called the image of a matrix. But if, for example, we have pivots after the row reduction only in the first 2, then only those span all of it. And the third one is not necessary for the span of the chosen vectors to span all the column space. So the whole column space is, in that example, for example, spanned by only the first 2. So let's see, let's do the row reduction. So row reduction, if we subtract twice the first row from the second, we have 0. Then we have 2 minus 6, minus 4, but in Z5 that's 1. And then 2 minus 6, again, 1. I leave the first row for now. And the third row, let's subtract the first one 3 times. So 0, minus 8, which is 3. And 2 minus 9 is minus 7, which is 2. All right. So with this, and let's just check it. Minus 9 plus 1 is minus 8, which is 3 in Z5. And 2 minus 3 times 3 is minus 7, which is 2 in Z5. All right. And now if we are able to also get a 0 here, then we would have pivot columns. Pivot columns are defined as those that only have, basically it's the element in that row that only has zeros to the left of it and only has zeros below it. So we know there's pivots when there's this pattern. It goes like stairs down here. So here we should get a 0, and then we have it verified that even this one is a pivot column. So far this one is, because there's this element where left of it is no non-zero elements, and below it is only zeros. The same goes for column number 2. We have this one here, left of which is only zeros, and below of which we can find maybe only zeros, because we can subtract the second row 3 times from the third. So we can do that now. So let's see if it works out. So this is further. Let's do this step with the rows. So 3 times subtract seconds from the third. So we have 0, 0, and -1 is 4 in Z5. So we have 0, 1, 1 here, and 1, 3, 3 here. So we see we have a pivot in all 3 columns. We have one here, here. And that means that all columns are pivot columns, in other words, basis columns. So we take the position and we see all 3 are required. So we refer back to the original matrix. All 3 are required to span it. So now there's more ways to denote it, but image of A, which we said is the same as column space of A, is spanned by the 3 columns, and we take the ones from the original matrix. We get the positions, we verify it by finding their pivot columns using the row reduction, and then we refer back to the original matrix. So all of these 3. Well, and because the dimension of the dimension of the matrix matches the Z5 to the third, that means the span of these 3 is actually the whole Z5 to the third. So that's a way to see that. And also we can verify this another way. We know that if the determinant is non-zero, then it's an invertible matrix, because we found actually here that the number of basis columns equals to the number of columns. So all are basis columns, all are linearly independent. It could happen that only 2 of them are, for example these 2 or something, and so, or maybe just 1 of them. Then we would not get these pivots here further down. So let's verify the determinant. What is its value? Well, we can take the matrix. We can, for example, expand it by the first row, and then we have this is the determinant for the 3 by 3 matrix. So that would give 2 minus 3 times 4 minus 6, so plus 6, and then 3 minus 6 minus 3 times 3 is minus 9. So this gives -1. So it's not 0 as was said. All right, so that further verifies that this is a regular matrix, meaning the columns are linearly independent, meaning all 3 columns are needed to span the column space. And what we are really talking about, we could take all 3 to span it even if they were linearly dependent, but what we are really looking at for here is the basis, the minimal generating set of vectors. So as few as we can take of the columns that will generate the whole column space. And we see actually, because all 3 are independent, we need to take all 3. So even the basis here, so the minimal generating set for the column space is exactly the 3 we took.